Hello. In this lab report, I will be discussing the properties and analysis of the gravitational force. I will be simulating the orbit of a star around a black hole using GlowScript code. Instead of collecting data and using a computational model to simulate the movement, we were given a starter code with the trajectory of a star and asked to find unknown values within the model. Using the concepts from this lab, you could find the mass of any object in space given the same information that we are provided with. The two relevant physics principles used in this lab were the momentum principle, or Newton's second law, and the formula for gravitational force. The momentum principle states that the net force is equal to the derivative of momentum with respect to time. For this lab, the only force that is present is the force of gravity, so it will be equal to the net force on the star. We'll also be breaking up the net force into parallel and perpendicular components, so we can observe the changes of each component as the star moves in an elliptical trajectory. The parallel component points in the direction of the object's momentum, causing a change in the magnitude of the momentum, while the perpendicular component points perpendicular to the momentum and causes a change in the direction of the momentum. The other relevant principle is the formula for gravitational force, which can be written as the force of gravity is equal to the gravitational constant, 6.7 times 10 to the negative 11th power, times the mass of each object interacting with the other, and divided by the square of the distance between the two objects. During this lab, the star travels in an elliptical path, so the distance and direction between the black hole and the star will be changing. Because we know this, we can determine that the force is non-constant and that it will change as the star orbits the black hole. In the code, we will represent this fluctuating value by calculating the net force at smaller intervals of time. For this experiment, we are assuming that the black hole has much more mass than the star, and therefore will not move at all due to the gravitational attraction. To output the correct values for mass, velocity, momentum, and force, there were many changes that were made to the starter code. The first change was typing in my Georgia Tech email address to the seed function to randomly generate a mass of the black hole. Later on, we'll use the computational model to solve for this unknown mass. Next, I changed the mass of the star to match the value that was provided in the lab instructions, and set the change in time equal to the number of seconds in a day. This was also directed in the instructions. The value of t was set to start at 0 seconds and will increase as the program runs. This section of the starter code uses calculus to compute the velocity of the star in both x and y directions, and the variable t is set to increase by the amount that was already specified. Then, the equations for initial and final momentum were added by multiplying the mass of the star by the velocity at both instants. The equations for the change in velocity and the change in momentum were also inputted. Using those equations, I was able to define the formula for the change in momentum and therefore also the net force. This is a direct representation of the momentum principle. The next few changes show the derivation of the parallel and perpendicular components of the force. As you can see in line 186, the net force is equal to the sum of the two components. Then, it's time to use the values that have been found to solve for the unknown mass of the black hole. By rearranging the formula for the gravitational force, this equation finds the mass, and the code will generate the value of the mass while the program runs. This code has been edited to generate arrows that show the net force and its components. The scale was changed so that they appear as a reasonable size. This is the full GlowScript code. You can see all the changes that have been made to generate the correct motion. The black sphere in the center represents the black hole that we're analyzing, and it is placed at the origin of the system. As the star moves, it travels in an elliptical path due to the gravitational force between the star and the black hole. The orange arrow represents the net force, and it always points towards the black hole because the gravitational force is acting in that direction. The magenta arrow shows the parallel component of the net force, and it points in the direction that the star is moving. The blue arrow is pointing perpendicularly to the motion of the star, showing the perpendicular component of the net force. To complete the goal of this lab, we now need to find the mass of the black hole. While the code was running, it was constantly generating values for the mass. This is a small portion of the output, and you can see that the values are very similar. They can be averaged to find the actual mass of the black hole, which was calculated to be 8.01 times 10 to the 33rd power kilograms. Let's talk about the difference between the net force and the change in momentum. As I described earlier, the momentum principle equates the two vectors, so they are numerically equal in magnitude and direction. However, the two values are actually different in concept. The net force is causing the change in momentum. A force acts upon the system by its surroundings, whereas a change in momentum is a way to describe the force's effect upon the object's motion. Likewise, the components of a net force are responsible for creating the components of the object's change in momentum. Lastly, we need to address the idea of replacing the black hole with a different one in the same location. We are given that the motion data for the star remains the same and asked if it would be possible to find a different value for the mass of the black hole. The answer to this question is no. If none of the values used in this lab to determine the mass changed, then it would be impossible to calculate a different mass for the black hole. Thanks for listening.